In order to make our task easy for calculating the hydraulic power, because we have so many steps, we have 1, 2, 3 up to 10 steps that we need to pass through in order to obtain the hydraulic power. I have put them in a Octave script file. I will just explain that, and then I will leave it to you to explore it, and I will also keep that script file in the resources section. So I have here, this is a text file. Look at the name hydraulic_power.m. It is a M file that can be opened in Octave and run in Octave. You can also probably use it in MATLAB with minor modifications in syntax, but essentially it should be able to work well in Octave. So this file calculates the hydraulic power required to pump water. Clearing all the variables, I have broken down the script into 3 main parts. The first part is specifications. You have to give the input specifications taken from the field and the users. Then there are some unit conversions. You see that not all the input specifications are in SI units. That is because the user is conversant in a particular set of units. Like as I said, the discharge volume, even though we need to finally express in meter cube and use the formulas, various equations in SI units, the input is in the form of liters for discharge volume. Sometimes it is in the form of liters per second for the discharge rate. The lengths, like the suction head, delivery head, are most of the time given in feet, and the dia of the pipe carrying the water is given most of the time in inch. So these are what you would call common usage. So getting the user inputs in the commonly used units in that neighborhood, you take it and do the conversion. You will have to do the unit conversion such that everything is expressed in SI units, and then you apply the hydraulic equations. Then I have a fourth part, which is the display. So you display then the results in an appropriate form. So let me just explain to you the script so that it will be convenient for you to use when you want to explore it. So I have here QL. QL is the discharge volume in liters, because most of the time we get the value in liters. dt is nothing but delta t, it is the time, discharge time. Dia is the inner diameter of the pipe. It is normally given in inches, so you will have to convert it to meters. LF is the total overall length of the pipe, including the horizontal part, vertical and the horizontal part. Nu is the kinematic viscosity. You will have to look into the science tables. It is a function of temperature. So at 20 degrees Celsius, it is 1 into 10 to the power of minus 6 meter square per second. At 50 degrees centigrade, I mentioned earlier, it is 0.55 into 10 to the power of minus 6 meter square per second. So look into the science tables to get the kinematic viscosity value. Epsilon is the height of the surface bumps. HSF is the suction head given in feet. HDF is the delivery head given in feet. G is of course the acceleration due to gravity, and rho is the density of the fluid. Here it is water, which is 1000 kg per meter cube. Now we come to the unit conversions. So in unit conversion, Q, the discharge volume, has to be converted from liter to meter cube. So it is QL, which is expressed in liter, by 1000 will give you discharge volume in meter cube. D the inner diameter, you take the value which is given in inches into 25.4 by 1000. We'll convert it into meters. Area is pi d square by 4. If you take the value d in meters, then A will be in meters square. The total pipe length, including the horizontal part, which is given by LF in feet, converted into meters by multiplying it with the factor 12 into 25.4 by 1000. HS, the suction head in meters, would be HSF, suction head in feet, into 12 into 25.4 by 1000. Likewise for the delivery head. Once you have converted the units, now everything is in the SI system of units. You can now apply the hydraulic equations. ED is the roughness ratio, which is equal to epsilon by D, and D, if it is in meters, multiply it with 1000 to express in mm, because epsilon is in mm, and express D also in mm to get the roughness ratio. Q dot is Q by dt. If you use Q in meter cube, then Q by dt will be meter cube by per second. U is Q dot by A. Then R, the Reynolds number, which is U into D by nu. Once you have all that, you can now use the Colebrook function which we developed earlier to obtain the friction factor. The inputs to the Colebrook function is the Rayleigh number and the roughness ratio. Once you have the friction factor, you can obtain the head due to the friction loss using the Darcy-Weisbach equation, F into L by D U square by 2G. Once the head due to friction loss is obtained, the total dynamic head is obtained, which is delivery head plus suction head plus head due to friction loss, all expressed in meters. Then the hydraulic power is rho into G into Q dot into the total dynamic head. So in this way you can streamline the process of designing or obtaining, estimating the hydraulic power by appropriate scripting in Octave, and then you can output the values you want to see. So I have used fprintf, and first the specifications, all the variables related to specifications in the user units and the SI units. Both you can express so that you will be able to compare. And then the hydraulic variables like the roughness ratio, the discharge rate, all in SI units, pipe fluid velocity, Reynolds number, friction factor, head due to the friction losses, total dynamic head, hydraulic power and energy. So all these things can be obtained just in. So the borewell example that we just now discussed, I have put in those values here, and all I have to do is hydraulic power. I will run that. You will get the output. You see that we had calculated something around 6000 watts hydraulic power requirement, and that's what you have got. You have the various parameters being displayed here. So I will leave this to you. I will leave this script file in the resource section. You are free to explore it and then try to apply it and find out the hydraulic power for various installations.